My name is Professor Orata, and we have had a series of lectures. So we move to this lecture dealing with Joule-Thomson experiment. Joule-Thomson experiment. Joule-Thomson experiment, a very important experiment. And the basis of this particular experiment will come from our previous derivation in the other lecture, where we have this coefficient which we have not solved, that is del H, del P, T constant. Now, applying against those mathematical expressions for sorting out partial derivatives, which we had mentioned was the permuter and the inverter, which are fundamental and key in solving partial derivatives so that you get expressions which you can work with, we will apply the permuter to this expression so that you get del H, del T, del H, del T, del T, del P, and of course, in this particular case, P is constant, here H is constant. Now, this del H, del T, we remember is Cp, that's the isobaric heat capacity. So we have already come across that severally in all the previous lectures. Now we have this expression del T, del P, constant enthalpy. That is change in temperature with pressure and a constant enthalpy. If you look at that expression, the variables in there are very easy to measure. You can measure temperature, you can measure pressure very easily. But doing that under constant enthalpy, where the environment is under constant enthalpy, is the basis of this particular experiment. And so, how do we determine that coefficient empirically? That's experimentally. So to determine the coefficient del T, del P of H is the basis of Joule-Thomson experiment. And so the experimental setup for Joule-Thomson is very, very simple. Very, very simple. We have a porous ceramic kind of system. So we have an outlet through which gas can leave, and an entrance through which gas can come in. And then we have a porous ceramic. This is a porous ceramic. Gas can go through. Then we have gas coming in. Let's call it P1, gas coming in. And gas leaving, call that P2. And let's call this compartment 1. Let's call this compartment 2. And we have a temperature measuring device, can be a thermocouple or anything for measuring temperature. Let's call it a thermometer for simplicity. Measure temperature. And so what we are talking about here is we have this gas coming in, and of course we are doing this experiment under diabatic conditions. Under diabatic conditions, let's just keep that to remind us that we are doing it under diabatic conditions. And as you remember, adiabatic means that it's no heat transferred into or out of the system. So we have our gas coming in, we have gas in compartment 1, which is able to throttle or go through the porous ceramic, driving out the gas in compartment 2, and that's what we have represented as P2. I repeat, we have the incoming gas. This incoming gas acts as a piston. You remember the piston cylinder model in the PV work? So this incoming gas acts as a piston, pushing on the gas in compartment 1, which throttles or goes through the porous ceramic matrix or membrane, and when it gets in, it acts as a piston, pushing the gas in compartment 2 out. So that is a very wordy explanation. Let us have a schematic of representing that, what I've just said. So we are saying we have the incoming gas acting as a piston, pushing on the gas in compartment 1, which goes through the porous ceramic. Let's call that the porous ceramic. Porous ceramic. And the gas in compartment 2 is acting as a piston to be driven out. So we have compartment 1 and compartment 2. And of course, they are at some various temperature and pressure, various temperature and volumes here. So we have, let's call that volume 1 and temperature 1 for compartment 1. And let us say that we have a thermometer here, and we have a gauge to measure the pressure, pressure gauge. So we have a pressure gauge. So what are we saying? The gas coming in is acting as a piston, pushing on the gas in compartment 1, which goes through the porous ceramic, pushing the gas in compartment 2 out. So this is the first representation. So the final representation is now that when this piston has pushed the gas in compartment 1 to that end, this piston in compartment 2 acts as a piston to be pushed. This gas in compartment 2 acts as a piston to be pushed out. So we now have a situation where we have the ceramic once again, and again we have the measurements, temperature and pressure measurements. So the piston now has pushed out the gas in compartment 1, and it has throttled out, pushing the gas which was in compartment 2, which now acts as a piston to be driven out. Very important that you understand this concept. The gas coming in is acting as a piston, pushing on the gas in compartment 1, which goes through the ceramic, pushing out the gas in compartment 2, which now is acting as a piston to be driven out. And remember now, we talked about reversible and irreversible work in earlier lectures. This is an irreversible work. We are talking about irreversible work in this particular case. So how do you calculate the work in compartment 1 and the work in compartment 2? So the work in compartment, remember, to calculate irreversible work, we have W is equals to minus pressure external delta V. That's for irreversible work, the expression, which we derived in earlier lectures. And so the work in compartment 1 is simply minus pressure 1 into the initial volume is V1 and the final volume is 0. So that is P1, V1. And the work in compartment 2 will be given by minus pressure 2, the initial volume was 0, the final volume is V2, so that becomes, the final volume is V2, the final volume is V2, the initial volume was 0, so it becomes minus P2, V2. So the total work is simply the work done in compartment 1 and compartment 2. So we just add them up. So it's P1 V1 minus P2 is P1 V1 minus P2 V2. Now, remember that we did this experiment under adiabatic conditions. Therefore, going back to first law, we say that delta U from first law, remember from first law of thermodynamics, we say that delta U is equals to Q plus W. And so since it's adiabatic, that means that there's no heat transferred into or out of the system. So we can put that Q value there as 0. So we have delta U is simply equals to W. And what is the value of W? The value of W we have seen is P1 V1 minus P2 V2. So what we are saying is that delta U, that's the change in internal energy for that system, is P1 V1 minus P2 V2. But what is delta U? We have said delta is a measurable change. Du is infinitesimal change. So it simply means that it is the difference between the internal energy in compartment 2 minus the internal energy value in compartment 1. So we have U2 minus U1 is equals to P1 V1 minus P2 V2. So if we collect the like terms, that is the ones together, the twos together, then you have U2 plus P2 V2 is equals to U1 plus P1 V1. But if you look at that expression, you are familiar with it now. We had said that H is U plus PV. So all this means is that is H2 is equals to H1. So what's the import of that? It means the enthalpy in compartment 1 is the same as the enthalpy in compartment 2. So whatever measurements we are made of temperature and pressure in compartment 1, measurements of volume in compartment 1, and that in compartment 2, those measurements of temperature and pressure are being done under constant enthalpy condition, which was very fundamental in that coefficient del H, del P, where we started off with, and we had the expression del T, del P, and a constant enthalpy, which we were to determine. So the temperature measurements, which we conducted in compartment 1 and 2, and the pressure measurements in compartment 1 and 2 were done under constant enthalpy conditions, which we talk of as isenthalpic, not isoenthalpic. You're used to isobaric for pressure, isochoric, so you don't talk of isoenthalpic. You say this is an isenthalpic process. In other words, done under constant enthalpy. So whatever measurements we have made them under constant pressure, under constant enthalpy. Measurements of temperature and pressure, we have made them under constant enthalpy. Now, in the limit of very low pressures, why low pressures? You know that gases behave as ideal gases in the limit of low pressures. That is, P, pressure tends to 0. So in the limit of low pressures, this coefficient now, which we have determined there, the limit of low pressures, that is as pressure tends to 0, is approximately, accurately measuring delta T, delta P. And this ratio here, delta T over delta P, is what we call Joule-Thomson coefficient, denoted as mu JT. That is the Joule-Thomson coefficient. That's the Joule-Thomson coefficient. Very important quantity. Joule-Thomson coefficient, you find it in handbooks of science and engineering. So this is a very important coefficient. What is the significance of Joule-Thomson coefficient? Suppose Joule-Thomson coefficient as a positive value. Then, all it means is that delta T, mu J as positive value, means that delta T is positive and delta P is positive. Or it can be delta T is negative and delta P is negative. Then you have mu J as positive. So what is delta T as positive? Simply means that the final temperature is greater than the initial temperature. Delta P being positive means the final pressure is greater than the initial pressure. So what does that mean? If final temperature is greater than initial temperature, then that's a heating process. And if final pressure is greater than initial pressure, that means the final volume is less than the initial volume. This is a compression. So this means that a gas with a positive Joule-Thomson coefficient can hit on compression. So you can work with one where we have delta T as negative. That means T final is less than T initial, and delta P is negative. That means P final is less than P initial. Then you can do the interpretation. In that case, you will see that it actually cools on expansion. And so Joule-Thomson coefficients are very important quantity, very important quantity in science and engineering.